feel like we have a smaller than normal cadre.
I was going to say the same thing. I feel like we're missing a lot of people. Not a lot, but like 2 or 3.
We only have 17 people in the class total. But yeah, we should have like 8 people in here. We only have 6. Oh, if Sky's in here, then I put Travis in here too.
Sky was in class this morning, right?
Yeah, I saw him earlier. Okay. Welcome back to Systems and Controls. Let's do a quick recap of what we've talked about past few days. What have we been talking about? What? Brilliant.
Stresses, different kind of stresses.
That is machine design.
I got the wrong notebook.
Yeah, that's. I mean, hey, way to pay attention in that class, but yeah.
I just looked back and just got the wrong notebook. That's really what's screwing me up here.
What have we been talking about the last 2 days? We've been talking about forces, particularly. I can't hear you.
External, boundary, inertial, spring,
We've been talking about inertial forces, spring forces, capacitive forces, resistive forces, energy dissipating forces. It's really dark up here. Wow. Wonder if that makes it any better. Not kind of. It's more colorful. We have been talking about mechanical systems. Okay? The whole goal of making... Oh, okay. Apparently Sky and Travis are not in this class. Apparently they're in the Thursday class. I don't know. I don't know who's here, who's not. Who's? Oh, okay. Casey is supposed to be here.
Casey and Mason, that's what it was.
Okay. All right. For mechanical systems, what we're dealing with is ultimately we're looking at, for translational systems, we're looking at how forces and displacements interact. Okay? Usually we're solving for some kind of a force, or maybe we're solving for the displacement itself, or maybe we're given the force. But at the end of the day, when we're looking at the translational system, we're looking at how does the system as a whole behave when you have multiple components all interacting with each other. We talked about modeling these systems, et cetera, et cetera. We also talked about rotational systems. That was on Thursday. So if we're talking about forces and displacements for translational systems, what are we talking about for rotational systems? We're talking about torque, or moment, and what else? Angular displacement. Okay. And the whole goal of talking about this, nope, I'm getting ahead of myself. The whole goal of talking about this as a system is how do we model the way that a system behaves? Now, the word behavior takes a specific context in this class. Does anybody remember why the word behavior means something? Specific to this class. Digging deep. I'm going back to first week. What is special about the word behavior? It is the output. Good job, Sam. Okay. This is system or component output. Okay. Which means the whole reason why we're looking at these translational systems, rotational systems, today we're going to be covering electrical systems, is because we want to know how the systems output things. How do we model the output? How do we determine mathematically what that output's going to be? All the equations that we're developing right now, they're important to understand because they describe what the output is. So for various systems, this also means your output and your input, well, your output has to be a function of your input. Okay, so for systems, output is equal to output as a function of input. Okay, and this is the whole reason why we're trying to model these systems. We're trying to come up with what is the relationship, what is the function that defines the output in terms of the input. Okay? For the translational system, the output was displacement, acceleration, velocity. It was a time-varying displacement function. The input was forces. For rotational system, you may have the output actually be angular displacement, and the input be torque, but you may have that be the opposite direction. You may have the input being angular displacement and the output be torque. You could easily switch those around. Okay, maybe not easily. That was a lie. You can switch those around. Okay. Good job, Casey. The whole reason why we're studying this, again, is just we want to know how, if we understand what the output and the input is, and we understand what the relationship are between them, we can adjust that as to give us some control over how the system is behaving, or as Sam said, how the system is outputting everything. Okay? The overarching goal is understand this relationship so that we can control it. Okay? We as humans like to control everything. All right, so the system that we're going to be covering today is the electrical system. So far, we've talked about translational and rotational systems. We have talked about the relationships between these. Again, with this being input and output, both of these are connected because they are related to work. A force times a displacement is the formula for work. That's what it is. Torque times angular displacement is the formula for work. Okay, so when it comes to electrical systems, what two components multiply to be work, or energy, or power? What's the formula for power in an electrical system? Power equals V times I. Now power is just the time derivative of work. It's work done per second or per time unit. When it comes to electrical systems, we are once again modeling these variables because they influence work being done. They influence the power. So, input or output components here are going to be voltage and current. Okay? Again, the relationship comes because they dictate power. The whole reason we look at these is because they dictate power. These, power. Those, power. Everything has to do with power. In any system, the transfer of power, whether that be from a translational system to a rotational system, or even from an electrical system to a rotational system, such as when you have a rotary motor, a DC motor. What a DC motor is doing is it's converting this kind of power to this kind of power. And now you have all new equations. But we'll get into that in the next lecture. When it comes to electrical systems, we still have our three forces, so to speak. We introduced them as forces in translational and rotational systems. They still exist as forces, but it's a force in a different sense. Okay? Here, the voltage is the equivalent of what a force would be, and the current is the equivalent of what a velocity would be. Okay? That's kind of what their equivalents are. You can think of them like that. Now, note, current is not a displacement, it's a velocity, which is why these two multiply to power and not work. In any case, when we are changing the force, what that means is we have, instead of having an inertial force, we now have an inertial voltage. What was the inertial force for a translational system?
The second order displacement relationship.
And it is most influenced by what property? You are correct. You're reading off the notes. But what's the formula for it?
Mass times some acceleration.
Mass times acceleration. So you said the second order differential part, that's the acceleration. The property that influences it was mass. Okay? So the inertial force for a translational system is mass. For a rotational system, it was the rotational inertia, which is basically mass at a distance. Okay? So what is the effective mass when it comes to voltage for a system like this? Anybody have a guess? You have three components that we talked about in circuits extensively. If you take a guess, one of them will be right. Resistance is one. I guess let me go ahead and write all of them. We got the resistive voltage, because this is, or dissipative. And then lastly, we have the capacitive, or energy storing voltage. And here all I'm doing is I just took the word force and I wrote voltage. So, okay. This one's the hardest one to guess because it doesn't have the name in it. Sam, what do you think this one is? It's got the word right in there that you just said. It's a resistor. Okay? The key point to a resistor is power that is used across the resistor gets transformed into what? It goes into heat. Hoping that, yes, you can see it. Okay, so resistor produces heat. What component is related to the capacitor? Dang it. That one was easy anyways. So the idea behind a capacitor is this stores energy in an electric field. Or I'll say power. Stores power in an electric field. Okay? It's actually storing electrical charges being the integral of current. So again, it's the velocity type relationship. Whereas springs store power by having a deformation, a physical deformation. Capacitors store power by having a buildup of charges or having a current integral over time. Now, the last component, does anybody remember what the inertial voltage is caused by? We got a capacitor, we got a resistor. What's that last one? Huh? It's the inductor. Okay? And what the inductor does is it actually stores power in a magnetic field. Okay? This is similar to, if we go back to our mechanical system, the inertial force was caused by changing the kinetic energy. Here, we are now changing the magnetic energy, where the magnetism is the relationship. It's the analogy to what the mechanical system is. So these are our three components that we're dealing with. These three are going to create voltages, and they're going to influence the system. So when we plug them all in, man, there's quite the sound show going on outside. Those are some very dangerous fireworks. Well, let's say we've got a power source, which I'm just going to go ahead and say that's P because it could be DC or AC. And then we got one of these, we got one of these, and we got one of these. This is the nightmare that I forced all of you to go through last semester. Here you got your power supply, here's your resistor, here's your capacitor, and here's your inductor. Okay? Resistor is measured in ohms, capacitor is measured in farads, inductor is measured in henries. Now, the guiding equation for coming up with mechanical system formulas was Newton's law, specifically Newton's second law. Force equals mass times acceleration. You sum the forces, then you can figure out what the acceleration is. Okay? That was the equation that we used to come up with all of our mechanical system equations. What equation are we going to use here to come up with our equations? How do we come up with equations for a system like this when everything is electrical? Where do we even start? What's step 1?
Why are you dressed up?
Because I'm warm.
Why
Is you warm? Who's in here?
Hey, you want to show up on my live stream?
Yeah, can I?
This is Jenna. She's not in this class.
I don't like, where's the camera? Oh.
It's right there.
Jenna, where else do you see a camera sitting?
Well, I don't know. I need to talk to you later.
Okay.
Or sometime this week.
I'm right in the middle of class right now.
Yeah, I
but
know.
We can talk later.
That's why I said later.
Okay. We can talk right now, though, if you really want.
An internship. That's all I want.
Oh, okay.
But, Alaska.
Oh, nice.
No, I haven't. That's where I want it.
Oh, okay.
I haven't found it.
Oh, good luck. All right, Sky gave the answer. Sky says that it's KVL. Okay? The way that you produce equations here is with Kirchhoff's voltage law. You can also use Kirchhoff's current law. Those are the two kind of guiding equations here. Or KCL. How do you calculate KVL? For Newton's second law, the equations was you sum all of the forces together, and that equals the net force. Here, you sum all of the forces together, and that equals the net force. So for Kirchhoff's voltage law, you just take all of the sums of the voltages in a loop, but that is going to be equal to 0. Okay? Otherwise, you could say, just like Newton's law, this is equal to the inertial voltage, the sum of everything else. Gosh, I'm just trying to teach here. Okay, so what we'll do is we'll go ahead and sum all the voltages in the loop. What are all the voltages we have in this loop right here? We got Vs plus, I'm going to go ahead and say Vr, plus Vl plus Vc equals 0. The voltage across the source plus voltage across the resistor, which I'm going to go ahead and make this a negative just because that's sign conventions for KVL. Vr, Vl, Vc. And some people will do this reverse where Vs is positive and these three are negative because they're passive components, but whatever. This is how I learned it. Okay, so Vs produces power. These three consume power, and they all sum to 0. Sky is on his game today, because he totally got that one. Here's where we're at. Now what? Every one of these components has a relationship between voltage and current. Okay? Every one of the components for every one of the systems so far, the inertial force had a relationship between force and displacement. Now it was a second order displacement, it was an acceleration, but there was still a relationship that came in the inertial force in the form of force is equal to some formula that has to do with displacement. Okay? So just like that, voltage and current have relationships for each one of these components. Here, Vs is our forcing function. This is our applied force or our applied voltage. What is the relationship between voltage and current for a resistor? It's current times resistance, which is Ohm's law. Okay? So here it's the current through the resistor times the resistance of that resistor. And that's the voltage. We have the relationship for the voltage through the inductor, which is L times the derivative of the current through the inductor with respect to time. Again, good job, Sky. And then for the capacitor, this is an integral relationship. 1 over C I dt. IC dt. This is the formulas that we have to deal with when it comes to these types of relationships. So when we come up with this once again is a second order system. Just like we were dealing with mass times double acceleration plus C times single displacement plus K times displacement. Just like each one of these were forces that were set equal to some forcing function. Here, we have each of these now having a relationship with current that all sum towards one type of forcing function. These formulas are the same, just with different variables. That's it. Vs is equal to, let's see, I'll take L di dt, because since they're all in one loop, IL is equal to IC is equal to IR is equal to IS. Since this is true, we'll just say it's equal to I. So when I write I here, it's the current through everything. L di dt plus I times R, make that a little I for funsies, plus 1 over C integral I dt. We can take the derivative of all of this, and then you get dvs dt, which is just a different function. We can call this fs if we really wanted to, is equal to L d squared I dt squared plus di dt r plus 1 over C times I. Which, if we're going to go with our naming convention up here where we put in dots, then this means that Fs is equal to L I double dot plus I dot R plus plus I C. These two formulas are identical. And guess what? The math to solve both of them is identical. No shocker there. So it's really not that surprising when we're looking at this type of a system that here, this is your inertial force or your inertial voltage. This is your resistive force or your resistive voltage. And this is your capacitive force or your capacitive voltage. Here, your capacitive force has the same form as the capacitive or energy storage formula here. Okay? There is no derivative here. This is a direct relationship between X and F. Similarly, this is a direct relationship between the current and F. There is no derivative relationship. The dissipative, or the energy dissipating portion, has a single derivative in it. And that is directly related to F. Similarly here, this has a single derivative in it, that's I dot. Deep. Okay, has a single derivative relationship to f of s. And that's for the dissipative. And then lastly, the inertial has a double derivative relationship with f of s. Okay, so we have the same components. They even land in the same place. The math behind them is identical. Now that's not to say that every single electrical component falls neatly into these three categories. Believe it or not, they don't. And not every physical component neatly falls into all three of these categories too. Again, when it comes to friction forces, like dry static friction, it doesn't nicely fit into this. It's a force that is produced that has nothing to do with displacement, or velocity, or acceleration. It is a force that just exists. It's much like diode. Power dissipation just exists. It is a constant value that we can't really control or change. That's it. Now you can actually change it, but once it's there, it's there. So when we're looking at these types of systems, we're looking at the same thing as what we were with mechanical systems. The math is identical. The setup is very similar. The multiple components here are identical. Again, we're just dealing with the same system. It just has the word electrical in it this time. Okay? All right, we're going to do a fun example. And check how much time I have. I am swimming in time. Okay, so let's say I've got a power supply, I've got a resistor, and then I've got this resistor branches out to a capacitor and to an inductor. How do I come up with the math equation for that? What is step one? We're not really going to be able to simplify here because we can't combine any of the resistors or capacitors or inductors. But that would have been step one if we could. So there you go. We're going to start with KVL. Okay. KVL isn't going to give us all of our equations here. KVL is going to give us an equation. So here we have two loops that we can go through. Okay, this loop one goes up like this, goes down like this, and then goes across like this. Okay, so we have Vs, which is negative, plus Vr, plus Vc equals 0. That is equation 1 from KVL. Equation 2 from KVL, what's different? You're using an inductor instead of the capacitor. So equation 2 is negative Vs plus Vr plus Vl equals 0. And here, if you really want to consider this a third loop, which technically you can just call this a loop. But then what you find is that Vc is equal to Vl. But you could get that by combining these two equations, if you really want to. Okay, so Vc equals Vl, and then we have these equations. But we don't really understand the entirety of this system yet. In order for us to really understand it, we also have to do some KCL. Okay, so I'll go ahead and throw node numbers on here. Here's 1, here's 2, here's 3. if we do KCL at node 1, then what we have is IS, which is the current coming out of the source, is equal to IR. So input equals output. Equation 2, our input equals output. So the input into node 2 is the current through the resistor, IR. And the output from node 2 is what? You see what? I'm sorry, Sam. You had a good answer. I just had to be a jerk. It's IC plus it's IC plus IL. Okay. So that's fun. We now have. And then we can do it at 3 too. Again, if you really want to. At 3, IC plus IL is equal to IS, which you can derive number 3 from the other two equations, just like we did it over here. For that third mysterious loop, you can derive it from the other two. This one, you can derive it from the other two also, because it's just this is equal to this, but we already know that equals that. So it's not a unique equation, it's just another equation, if you really want to have it. I'll even label this one just for funsies. All right, so now we have all of the equations that we can use for the system. This is akin to writing out some of the forces and some of the moments. That's it. Some of the forces and some of the moments. Okay. So if we wanted to solve for the voltage across, say, the capacitor, how would we do that? Huh? We're gonna have to combine a bunch of these equations. You're right. And we're gonna have to use what we know. We're gonna have to just continue to play with a lot of math. So if we want to find VC equals something, at the end of the day, we're looking at the whole purpose of analyzing systems is to understand the behavior. What is the behavior again? It's the output. We need to have the output as a function of what? The input. Here, VC is going to be our output. We need to have our output VC as a function of what's the input? What is the input to that system? It is ultimately Vs. This is the input. But it changes the entire system based on the current that travels through the system. And the current is ultimately what is going to create a lot of the equations for this system. We're going to come up with an equation for Vs. Well, for VC in terms of Vs, but we have to understand how current changes in the system in order to do so. Okay? So, our ultimate goal, come up with a nice equation. Let's start doing that. All of our equations here link voltages and currents. These two are related because we know that each one of them inside of each component has a relationship between current and voltage. Every one of them does. So we got to use those mixed with our three equations. VR equals IR, R. VC is equal to 1 over C, integral of IC dt. And VL is equal to L, DI, L, dt. Okay? This is all the equations we need to solve. That's it. I covered those first day of class in electronics, and then we just did it over and over again the entire semester. We're doing it again right now. You have all the equations. They're not hard to come up with. These relationships are hard to remember sometimes just because they're gross. But we have everything. So if we're trying to solve for VC, which one of these formulas should we use? This one?
Never mind.
This one?
Yeah.
This one?
That one.
This one?
Yeah.
Why would you pick this one?
It has VC in it.
It has VC in it, yes. But why else would you want to pick that one?
Does it have VS in it?
Because it has VS in it. And this is ultimately the input to the system. So yes, you were right. Just thanks, Brandon, for the little bump. This is what we're going to do. We're going to start with this equation because it has both of the components that we want. The thing that we don't want is this thing. But this thing ends up being a function of this and this. Just like when we were looking at the suspension, the force through the axle ended up being a function of the suspension above it and the suspension beneath it. It wasn't a constant value. It wasn't something that was independent. It was a system characteristic that depended on the behavior of the whole system. VR is a system characteristic that depends on the behavior of the whole system. If we're trying to solve for VC, VR is dependent on VC, just like VC is dependent on VR. That's why they're right next to each other in this equation. They depend on each other. They're influenced. They're interrelated strongly. There is only one solution to this system. And then in order for us to find it, we have to look for what is our output variable, what is our input variable, and we have to get everything else in terms of those two. So that we only have an input and an output variable in the equation. Okay? That is what system analysis is. Input to output. How do they correlate? Okay? So, Sam picked this one. This is the right one. VS is equal to VR plus VC. This one we don't want, because it isn't in terms of either the input or output variable. So, what do we do? Jackson's pointing at the board menacingly. Or at me, I can't tell. Is that pen aimed at me or? Okay. I'll stand a little bit further back into the corner. The first thing that we should do here is we need to get VR in terms of VC. So we need to get VR is equal to some VC as a function of, well, VS, really. Some function of VC is VS. So what we got to do is let's mess around with VR. We know that VR is equal to IR. VS, this is already in the form we wanted it. We don't have to change it. VC is already in the form that we wanted it. We don't want to change either of those, because we already have an input and an output variable already in our equation. But we do have this IRR, and that is not an input or an output variable. So let's keep playing with it. What equation do we have that says anything about the relationship between IR and IC? We got the KCL. We have this one right here. We have number 2. Okay? So if I say KCL number 2, I'll just go ahead and write that. IR is equal to IC plus IL. We're going to go ahead and interject that in. We will replace IR with that formula, and we get VS is equal to IC plus IL R plus VC. Okay, this is gross. Why is this gross? This, we can get this in terms of VC. We have that equation right here. What about this one?
Can't we put it in terms of the source?
What do you mean?
I don't think we put IL as IC plus IL equals IS.
I mean, we could, but IS is going to change based on what the system behavior is. We don't have a nice, neat formula for IS. But, I mean, that's a good point. That's unfortunately like saying, you know, the force to the system is the relationship of the height of the system as it moves. But the height of the system depends on all the components that are in the system. So it doesn't make it, it would be more of an output than an input there. What we're going to do is we're going to say, okay, this IL does depend on VC somehow. We know this depends on VC somehow. We know this has to depend on VC somehow. We'll figure it out. So VS is equal to, IC is equal to 1 over C integral of IC, whoops. That is not what I meant. Sorry. I was writing this exact formula. If we're going to switch this around and solve for VC in terms of IC, IC is equal to C dVC dt. So this is equal to C dVC dt. Now the nice thing is we now have IC in terms of VC. We just use this relationship right here, that formula. But we still have this IL. Okay? IL has to depend on VC somehow. So what we're going to do is we're going to say, well, we'll do the same thing down here. IL is equal to 1 over L times the integral of VL dt. So this becomes plus 1 over L integral VL dt times R plus VC. Have we gotten any closer? Well, we have, just not recognizably so. Do we have any relationships between VL and VC? Huh? They're equal. We have equation number 3 down here. They're equal to each other. So we are closer. All we have to do now is bring in KVL number 3, which is VC equals VL. And as soon as you do that now, VS is equal to C dVC dt plus 1 over L times the integral of VC dt times R plus VC. Now in order to get this into our nice differential formula, we can take the derivative of both sides. Okay, so the final answer ends up being, okay, I can't see the bottom of the board. The derivative of the voltage source is equal to CR, I'm going to bring the R in, multiply it here, times d squared VC dt squared plus 1 over L times R, going to bring the R in here too, times VC, because VC is the derivative, plus dVC dt. This is our differential equation now. Jackson says no. Yes, it's gross. Yes. I am aware of that.
Is that a plus or a T before R over 2?
It's a plus. And this is not a 2, it's an L. Yeah, that's that L. All right, so that was fun. You guys want to go over another example? Tajay says yes. Jackson says no.
No.
Okay, so you're willing to do this on the homework then? You might want to do another example if you don't know how to do this on the homework. You had the right mentality. Applaud you. Okay, again, for right now, we are only focusing on how to develop this is some input equals some function of the output. The solution to this problem ends up being VC equals VC as a function of VS. That is the solution to this equation. This equation right now is the input is equal to some function of the output. It's a little backwards. It takes differential equations to flip that. But this is why we care about this. Every variable we have in here is either VC or time. Every variable we have over here is the input to the system, which is VS. Okay? So we'll do this again. And this time, I'm going to be just as mean. Should start on this side of the board and work that way. That makes the most sense. So, example. Okay. Ooh, I'm no longer swimming in time. Let's say we have a voltage source here. The voltage source is connected to a resistor, where the resistor then connects to a resistor and a capacitor and an inductor. Let's say our input variable is what?
Yes.
It's VS. You know what? Let's change this up. We're going to make this be a current source. IS. Because I can. And because we've done VS as an input a lot already. Oh man, this thing gets gross if I do that. I'm kidding. This is actually really easy to solve. So the input is IS. What is the output? It could be IC, it could be VC, it could be IL, it could be VL, it could be IR, it could be VR. well, I'm going to go ahead and say that, all right, Brandon, we'll make it IC this time. But we could have very easily picked any single variable in the system. That wouldn't have been a problem at all. Okay, so the output is IC, the input is IS. Great. I'm going to go ahead and call this one R1, this is R2, this is C, this is L, this is IS. How do we start? What is step one? KVL and KCL. That is our Newton's equations for electronic circuits. So we'll just go ahead and write down all of our equations because that's what we do. We end up using some of them. We don't use all of them. All right, where are we going to start with KVL? We'll say loop 1. We got to pick a loop. Well, what should our first KVL equation be? So we got negative Vs, which is the voltage across the source, plus R1 plus R2 is equal to 0. Okay, good job. What's our second loop equation? Plus Vc is equal to 0. See here, first loop, we go, we're a single electron. We're forced to go through this resistor. We choose to go through this branch and then go back. Second loop, we start here, we go through this resistor. We, instead of going through that loop, we go down and we end up back at IS. So the third loop is going to be we start here and we go over there and we come back. Negative Vs plus RT plus VL equals 0. Now, we can also create a loop right here, and a loop right here, and a loop right here. So I'm going to go ahead and label that equation 4, and that one's just going to say that if you combine these three equations, you get RL2. This is a VR1 and a VR2. This is a V. My apologies there. VRL2 is equal to VC is equal to VL. Okay? You could technically make that 6 equations if you really wanted to, because you can draw 6 independent loops there. But I don't want to because I'm tired. You'll also notice that these 3 equations can be derived from these 3 equations. It's not hard to figure that out. Those are all the things that we can come up with KVL. Let's go ahead and label our nodes. 1, 2, and 3. We will have 3 equations from KCL. Equation 1. IS equals IR1. What about equation 2? What is the input to node 2? It's IR1 again. Is equal to, what is the output from node 2? Yep. IR2 plus IC plus IL. And then equation 3, you can actually derive equation 3 from this. It just ends up being IR2 plus IC plus IL is equal to IS. Okay, those are all 7 of the equations that we have. We also have VR equals IRR. We have VC equals 1 over C integral IC dt, and we have VL is equal to L DIL dt. Okay? 10 equations. All of them count. Any one of them is fair game. We're just throwing equations at the board. Some of them are useful. Some of them are not useful. Great. So, what is the equation that we should probably want to start out with that links our input and output variables? KCL number 3 already has IC, which is what we're looking for, the output, and it already has IS, which we're looking for is the input. So, just going to go ahead and KCL number 3, write that in. I'm going to start with IS on this side. IS is equal to IR2 plus IC plus IL. Now the issue that we're running into here is that we want a formula that only has input and output. But this is not the output and this is not the output for this equation that we have selected. We picked IC. So what do we do now?
Just make IS equal to IR1.
I mean, you can. That doesn't help us out because it gets rid of our input variable. We need to try to get IR2 as some function of IC. Okay? We're looking for IR2 is equal to some function of IC and maybe the source voltage too. But we're also looking for this current through the inductor as a function of IC and potentially IS as well. If we can find those, we will replace these variables with IC and IS functions, and then we will only have inputs and outputs in the system. That's it. Okay? That is our ultimate goal. If we can figure out what these functions are, we'll plug them in here, we'll be done. How do we find those functions? What did we do last time? In a KCL equation, if you start interjecting other one of the KCL equations, you just derive the other ones. So, like if we plug in IR1 is equal to IS, you get this equation. If you plug in this equation into that, you get this equation. So we can't use KCL. These two equations aren't helping us right now. We don't have voltages listed in our system yet. The only thing that helps us are these three equations. Which of those three equations can we use? We can use this one, and we can use this one. Because we have an inductance and a resistance in that formula. So we'll go ahead and we'll input Ohm's law, we'll input the relationship between voltage and current in an inductor. IS is equal to IR2 is equal to VR2 divided by R2 plus IC. This is already the variable we want it to be. It grew up and became the hero we all knew it could be. Plus IL, oh that's gross. IL is equal to 1 over L. So if I just rewrite this equation, IL is equal to 1 over L integral of VL dt. Integral VL dt. Now what? We have voltages now in this equation, which means we can now use KVL relationships. Every solution will require you to use both KCL and KVL because both influence the behavior of your system. Okay? So the reason why we had to change between currents and voltage is so that we can use KVL now. That's the whole purpose. Now that we have voltages in, now these three equations are fair game. Sorry, 4. And I'm going to really strongly emphasize 4. Which one of these equations should we use? Yeah. How'd you guess? We really should just use this one. Okay, they're all equal to VC. So all we have to do is say, okay, KVL number 4, we have VR2 equals VC equals VL. That's good. So now if we plug that in, IS equals VC over R2 plus IC, which is already there, plus 1 over L times the integral of VC dt. Now this is about to get super ugly. We now have everything in terms of the voltage across the capacitor, except for IC, which we could change that into this. What's the last step? Jackson says no. That's not a valid answer. This is not true false. Well, we will have to. That's actually the last step. So you're thinking ahead. Dang it. You answered my question right. I asked a stupid question. What is the next step? How do we get VC in terms of IC? We have one equation. So, using this equation here, IS is equal to 1 over C integral IC dt over R2 plus IC plus 1 over L integral of 1 over C integral of IC dt dt. Man, that's ugly. If you would have done this in terms of IL, it would have been super nice. But we didn't.
Or IL1.
Yeah. I hope you realize. Okay, so Brandon, for those of you who are listening online, Brandon just said we should have just done this in terms of IR1. Because if you would have done that, this is the equation. There's your input and your output right there. It would have been super easy. You realized that when you said that, didn't you? Yeah, dang it. Smart Alex in class. Good call, though. That was very observant. It's good for a laugh. All right, so our last step is we need to clean this up because this is a mess. This is gross. What we're going to do is we're going to take the second derivative of both sides, because what that's going to do is that's going to get rid of this double integral and put it in terms of just not a double integral. So d squared over dt squared is equal to, I'm going to go ahead and rearrange that so that it's a little prettier. I'm going to put this term out front, d squared IC over dt squared. Okay, second term is this one, 1 over C, the C and the R2 go together, so it becomes plus 1 over C R2 times DIC over dt. So that's this term just being put here. And then the last term, double derivative of this. Clear it up a little bit. We have 1 over LC times IC. And that is our system equation. We only have IC as a variable on this side. We only have IS as a variable on this side. The solution to this will look like this. IC is equal to IC as a function of IS. Thank you. Any questions over this? Have I thoroughly murdered your brains? Does this make a little bit more sense? Hey, you don't pack up until I tell you to. What time is it? Oh, dang it. I still have 1 more minute of your life. All right, well.
You got a lot more than 4 more minutes in my life. You got like another 2 years of it.
That's the right mentality. Okay, yeah, you'll have a problem over something like this due next week. You do have 2 homework assignments due this Thursday. One of them is a quiz. One of them is a reading assignment. Okay? They're due this Thursday at midnight. If you have any questions about those, please don't come to me Thursday at midnight. That is